So, again, assignment 5, that's due on Friday. And chapter 2 exam on exam 2, which covers chapter 4 and 5, is on Monday, from week from today. So questions on the assignment?
I had a question on 1B. About finding the just the best ways to find equivalence classes.
Well, now keep in mind that we're just looking at integer points. Okay, so if you take the integer point 1, 0, right, x equal to 1, y equal to 0, what's x squared plus y squared equal to?
1.
So what are all the other points where x squared plus y squared equals 1? All right, so on. I'm sorry, go ahead.
Just that one?
No. So 1b, right, so x, y is related to a, b when x squared plus y squared equals a squared plus b squared. Now, 1, 0, the equivalence class of 1, 0 is the set of all x, y, such that x squared plus y squared is equal to 1 squared plus 0 squared, which is equal to 1. So look at that equation. I mean, I hope that equation there means something to folks.
It's a circle.
Sure. So we want the integer points on that circle. Okay? So that's the circle of radius 1. So what are the integer points on that circle? I'm trying to, connect some intuition that you have, that you've used throughout your calculus courses and such, and, bring that to bear here so that we're talking about, that old knowledge that you have in a new way. All right. And then there's the other points. So there's 3 equivalence classes that were asked about. The 1, 1 equivalence class. X squared plus y squared is equal to 1 squared plus 1 squared, which is 2. All right, and x squared plus y squared equal to 2 is what? That's the circle of radius square root of 2. And, what are the integer points on that circle? Right? Not this point. I mean, this point is on that circle. Right? Because square root of 2 over 2 squared plus square root of 2 over 2 squared is 1 half plus 1 half, which is 1. But that's not an integer point. I just want the integer ones. And then the other one that's asked about is this one. Such that x squared plus y squared equals 3 squared plus 4 squared, which is 25. Right? And that's, that's the circle of radius 5. And it's got, so many integer points on it, in particular those with x and y being 3 and 4, or negative 3 and 4, or 3 and, or, 4 and negative 3, so on and so forth. Or 5 and 0, 0 and 5. Mm-hmm. All right. No proof necessary for what those equivalence classes are. Just draw them. Just draw them and show me the integer. Draw the circle, the whole circle, but then put the integer points on that circle.
Okay, so for like 1, 0, it'd be like label the points 1, 0, 0, 1.
Yeah, those are two of them.
Okay.
There's a few more.
Negative 1, 0, 0, negative 1.
Yeah.
Okay, so
That makes a lot more sense.
Sure. Write down the information that you have when you're trying to kind of make sense of what's going on. And, thoughts will then start to occur to you. I just did that writing down process for you. Again, it's one of those things where, what you used to do and what you're doing now, the practice of what you're doing is different. In your calculus classes or your differential equation class, they say, oh, okay, give me the solutions to this. Give me all the solutions to that linear differential equation. You look at it and you're like, oh, okay, I know what to do. It doesn't go that way here. You don't know what to do. You have to think about it. In particular, starting with definitions. All right, what else? Did I start the recording? I did. What else, guys?
I'm a little confused on number 3.
All right, so here the relation is divisibility. So A divides B. Oh, no, don't tell me I wrote that backwards. No, that's right. A times K is equal to B. A divides B. In other words, B is a multiple of A. So show that that's a partial order. So you got to show it's reflexive. Right? Show it's reflexive.
Asymmetric and transitive. Right?
Transitive. Yeah. So the only one there that... So actually showing anti-symmetry there is maybe, it's a little bit, well, I mean, it's not hard, but I mean, it's more involved than some of the other ones. Okay? So for number 3, right, A divides B when B is equal to AK, right, for some K in N, right, so reflexivity, right, so what, A divides A because what? A is equal to A times K, for which K?
1.
Period. Anti-symmetry. Right, so assume A divides B and B divides A. Therefore, right, because A divides B, B is equal to A times K. And because B divides A is equal to B times what?
L.
L, for some L. So now show that, K or L is equal to 1. Right? If you show that K or L is equal to 1, then then you're done. Then you get that A equals B. So blah, 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 blah. Therefore, A equals B. Right? And then show transitivity. And that shows that this is a partial order on the set of natural numbers. Oh, I didn't. So for A comma B in N, A divides B when. Right, so it's a relation on the natural numbers, including 0. You can include the 0 in there or not. 0 divides nothing, of course, and everything divides 0, so it's kind of not an interesting element of that partially ordered set, but you can include it if you want. All right, so show that's a partial order. Yeah. What else? All right, so please, get started on this if you have not done so already, and we'll answer questions again on Wednesday. Please don't leave it for Thursday night. It's just not going to happen for you if you do. Okay, well, not that it won't happen for you. It might not. In which case, I can't help you out too much because there's not enough time. Alrighty. So, just had one final example in this section. So remember we were talking about, for this chapter, we were talking about partially ordered sets. So it's a set with a relation. This symbol is usually used. And that set is a partial ordering when this relation is reflexive, antisymmetric, transitive. Right, remember, antisymmetric means x less than or equal to y, and y less than or equal to x implies x equals y. Transitive is x less than or equal to y, and y less than or equal to z implies x is less than or equal to z. All right. So the final example that we had was this partition lattice, as it's called. The word lattice, we haven't defined it. It's a special partially ordered set. So let's just recall that definition. Lattices are specially relations are not interesting in and of themselves. When you put conditions on the relations, then they become objects of interest. In particular, partially ordered sets. Lattices are specific types of partially ordered sets. In fact, every example I've given you is a lattice. Or no, actually, is the divisibility set a lattice? I think it is, yeah. It's a whole subfield of mathematics that people look at for various reasons. So the definition of a partition of a set A is a collection of non-empty subsets, A1 to AN, such that 1, each one is non-empty, 2, the intersection of any two is empty, and 3, the union of all those sets is A itself. So you're dividing A into disjoint subsets, right? And the sets A1, AN are called the blocks of the partition. And the number of blocks, of course, isn't always the same. So we define a relation on partitions by refinement. So partition A1 to AN is less than or equal to partition B1 to BN when A1 to AN is a refinement of B1 to BM, excuse me. That is, for every AI, there is BJ. So again, here's the stacking of quantifiers, right? For each I, there is J, such that AI is a subset of BJ. For every block of A, so for every block within the A's, there is a block within the B's, such that A is contained within B. Another way to think of refinement is, you take the partition B and you partition its subsets into smaller partitions. You break its subsets into smaller sets, and that's a refinement. Okay, so that's more of a top-down way of looking at it. This is more of a bottom-up, although in the abstract, this is a little bit easier to see. So the set of all partitions, we'll call it pi of A, and that relation is a partial order. So the example we had was as follows. Let A be 1, 2, 3, 4. The diagram for pi of A, Hasse diagram for pi of A is as follows. So you have the partition into one block, and covering the partition into one block covers all the partitions into two blocks. Right? All of these partitions into two blocks, of course, are a refinement of the partition of one block. Right? I mean, if you take a partition and you break one block into two, that gives you sort of what's called a covering relation. So this refinement is the largest refinement that's less than or equal to that. A largest refinement. That still is a refinement. Partitions from two blocks into three, and the covering relations look like that. Let's put the rest of them in. So 1, 2, 3, 4. Let's do them. Let's color code them. Since this is the interesting part of the PO set. So 1, 2, 3, 4. Right. This is a refinement of that. 1, 3. 1, 2, 3, 4. So the one containing 1, 2. This is a refinement of that. And of course, there's only going to be two partitions where you take these two blocks and take one of the two blocks and split it into two smaller blocks. Right? Because you only got two blocks, so you can only split each block one way. And then this one, 1, 3, either you break the 1 and the 3 into different blocks, and you get that. Or you break the 2 and 4 into blocks, and you get this. And then the 1, 4 through 2, 3, 1 and 4 into separate blocks, or 2 and 3 into separate blocks. And then this one, well, how do you see the covering relations there? Well, if you break this block of size 3 into two blocks, you're going to get two blocks of size 1 and one block of size 2. So just look at the block of size 2 here to see where the covering relations come. Right, so the block of size 2 could have 2 and 3, which is this one. Let's not do red, let's do blue. 2 and 3, which is that one. 2 and 4, which is, where is it? There. This one. Or 3 and 4, which is this one. This one here, 1 and 3, that one. 1 and 4 is this one. 3 and 4, that one again. This one, purple. 1 and 2, 1 and 4, and 2 and 4. And this one, some violet there. 1 and 2, not too close to that one. A gray. 1 and 2, 1 and 3, or 2 and 3, which is here. So there's that partition lattice for a set of size 4, and it only gets more interesting as you go on. By the way, notice this partial order has levels. Right, so the set that you're partitioning A has 4 elements, and that gives you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 partitions, and those partitions, split up into levels like this, right? 0 level, first level, second level, third level. Not all partially ordered sets do that, although this one does. So let's prove that that refinement is a partial ordering. Okay, so I was just talking about it, just examples here. So let A1 to AN be an element of the set of partitions of A. Certainly A1 to AN is less than or equal to A1 to AN, because for every AI is a subset of itself. Anti-symmetry. So let A1 to AN and B1 to BN be partitions of the same set. Assume that A1, the A's are less than or equal to the B. Partition for the A1 to AN is less than or equal to partition B1 to BM, and partition B1 to BM is less than or equal to partition A1 to AN. Okay, so we need to show that they are the same. Okay, because A1 to A, because of the first one, for every AI, there is Bj such that AI is a subset of Bj. Okay, so consider the set A1. So within that, I guess I shouldn't have erased that. Consider the set A1, the block, sorry, A1, in that partition A1 to AN. So consider the block A1 in partition A1 to AN. All right, because the partition A's is less than or equal to the partition B's, there is Bj such that A1 is a subset of Bj. Okay. Now, because the partition B1 to BM is less than or equal to A1 to AM, write it that way, because B1 to BM is less than or equal to A1 to AN, right? There is little k, A sub little k, such that A1 is contained in Bj, and Bj is contained in AK. So, we showed that the subset relation is transitive, so what does this imply? We showed that the subset relation is transitive, so what does this imply? Right. What does this imply? Because the subset relation is transitive.
AI is a subset of AK,
Right.
or A1.
A1 is a subset of AK. But what's special about the A's? The A's are a partition. So because the sets are disjoint, well, are pairwise disjoint, not all disjoint. What does this mean if A1 is a subset of AK? And, if K isn't equal to 1, then what?
BJ is a subset of AK.
Nothing about B just yet. But because the A's are disjoint, suppose K is 2. Could it be that A1 is a subset of A2?
Yes.
You sure? They're disjoint and non-empty. A1 intersection A2 is empty.
So no, they wouldn't be.
They can't be disjoint. They're not. The intersection is empty, but the sets themselves are not empty. You can't have this unless what? Pairwise disjoint and non-empty. Must have that what? I mean, disjoint sets, disjoint non-empty sets, you can't have that one as a subset of the other, because then they wouldn't be disjoint. So this means what? It's not a contradiction.
They're equal?
That K is 1. Yeah. Exactly. We must have that K as 1. Therefore, A1 is a subset of Bj, which is a subset of A1. So what?
So BJ is a subset of A1.
Even more.
It's a subset of all A.
So I mean,
BJ is equal to A1.
Bj is equal to A1.
Because BJ is a subset of A1 and A1's a subset of BJ.
Yeah, every element of A1 is an element of Bj, and every element of Bj is an element of A1. That means they're the same. Right. I mean that's how we prove that two sets are equal. A1 is a subset of Bj, and Bj is a subset of A1. Right. That's how we prove that two sets are equal. I mean, we just don't usually write it like that. This implies Bj is equal to AI. So A1, sorry. I shouldn't have said A1 actually. So consider not the block, but any block AI in the partition. because this is true, there is Bj such that Ai is a subset of Bj. And then because Bj's, or the B's are less than the partition into B's is less than or equal to partitions into A's, there is an AK such that AI is a subset of Bj is a subset of AK. Because the subset relation is transitive, AI is a subset of AK. However, because the A's are disjoint and non-empty, we must have that K is not 1 in this case, but I. Therefore, AI is a subset of Bj is a subset of AI, which implies that Bj is equal to AI. So every block of the A's is a block of the B's. In a similar fashion, we can prove that every block in the B's, just repeating this proof, exchanging A's with B's, replacing A with B also yields that every block of B1 to Bm is a block of A1 to Am. So every block in the partition into the B's is a block of the partition into the little A's, and vice versa. So they have to be the same partition. They're the same exact partition, because every block of one is a block of the other. And you're partitioning the same set, of course. So non-trivial. I mean, that's took a whole page to say it. This anti-symmetry deal with the partition lattice. And now we're not done. I mean, we still need to do transitivity. And transitivity is easier, actually. Okay, so suppose that partition A1 to AN is a refinement of partition B1 to BM is a refinement of partition C1 to CL. Right? So for every AI, there is, by definition, some Bj such that AI is a subset of Bj. Again, by definition, because the B's is less than or equal to the C's, there is CK such that AI, which is a subset of Bj, and Bj is a subset of CK. Therefore, for every AI, there is CK such that AI is a subset of CK, as required. So that's the end of that proof. Oops. So that's a really nice example of a partially ordered set. It's got a very rich structure. The study of partially ordered sets, in and of itself, is a whole subfield of mathematics. I know a lot of people who work in that field. It's not. I say stuff about it once in a while. It's not really my main research area, but it's closely related to it. So that's one of the very interesting ones, and the applications of such things are very diverse. So that's all for chapter 5. Okay, so all we've covered really is just what are just equivalence relations and partial orders. Equivalence relations, equivalence classes, and partially ordered sets. Just the definition of partially ordered sets. But both of them are very important, and they get a lot of play in mathematics. All right. So we need to move on to chapter 6. So chapter 6 is on a special proof technique in mathematics called mathematical induction. Has anyone seen it before?
I don't think so.
No computer science?
I've seen it, but we've never really delved deep into it.
No computer science students in the class? Because that's there's this introductory discrete math class that computer science students take, and in that we cover induction. So induction is, depending on what type of math you do, induction is more or less important. The type of math that I do, induction is almost everything. I remember one of my professors in grad school saying, "Yeah, the first 10 years of my career was just doing induction." The applications of induction are very, very diverse. It applies to any statement or structure that you build piece by piece. If you can build up some structure piece by piece in some way that you can describe it, then anytime you want to talk about that structure, you can talk about it using induction. And that's just sort of the basic idea of it. So anytime you're dealing with, computer programming, data structures in computer programming, or analysis of inductive type structures in computer programming, so all these control loops that you do in computer programming. Knowledge of induction is just very important because it's just the thought process that goes into these things. So here it is. So back to predicate logic. It's you can't explain induction really without understanding predicate logic a little bit. So we're going to go back to the notion of predicates and predicate logic and domains and quantification. So given domain n, so the basic domain over which you do induction is the natural numbers, although it doesn't have to be the natural numbers. Or any other domain consisting of a sequence of consecutive integers. With the smallest member. So, for example, if you had something like this, domain D equal to, so instead of starting at 0, you have to start for some reason at -2. Something like that. So you have this domain of consecutive integers, and you start at 0, or you start at 1, or you start at -2, or you start at 6, whatever it might be. You just have some starting points, and then you go consecutively after that. So given such a domain, mathematical induction is used to prove that statements of the form, well, to prove true, if they are true, statements of the form for all n, p of n over domain D. True over D, I guess just say. Statements of the form for all n, p of n. Okay, and the first principle of mathematical induction, so there's a first and a second. We call them the first and the second, but actually there's only one. They're logically equivalent to each other.
One quick question: is that P of n a power set, or is that just notation?
A predicate.
Oh, I see.
Yeah, predicate for all n, p of n. So some logical statement that uses n. All right, so I have n, I have 6 quarters in my pocket. I have n quarters in my pocket. Something like that. So the first principle of mathematical induction, excuse me, to show is as follows. To show that for all n, p of n is true over D equal to, so I'll start at 1 in this case, over this domain D, it suffices to show the following. One, P1 is true, and 2, for every n, Pn implies Pn plus 1 is true. So this first thing that you show is called the base case. And this second thing that you show is called the inductive step. Okay, now why does that work? Well, I mean, you show, so I don't want to really get into it. We're not actually going to show that mathematical induction gives you that this is true. We actually do explain that to computer science students, although we don't really hold them responsible for the truth of it. But intuitively, it's really quite clear. Why does it work? Let me do it in blue. Why does this work? Well, given P1 true and P1 implies P2 true, we get that P2 is true via direct proof. Right? P1 is true, and that's the hypothesis of the statement P1 implies P2. But we know that the statement P1 implies P2 is true, therefore P2 must be true, because true has to imply true for the implication to be true. You can't have that true implies false. True implies false is a false statement. Right? And then now, given P2 implies P3, we get P3 Now given P3 implies P4, I mean, we know P3 implies P4 is true. We get P4, etc., etc. Right? For every n in the domain, Pn implies Pn plus 1. So P1 is true, and P1 implies P2 is true. So P2's got to be true. But then P2 implies P3 is true. And because P2 is true, and P2 implies P3 by a direct proof, we get P3 is true. But we also know that for every n, Pn implies Pn plus 1. So P3 implies P4. But that's true. But since P3 is true, by direct proof, we get that P4 is true. And so on and so forth. So, you repeat that a gazillion times if you need to show that P of a gazillion is true. You only do it, as many times as you need to get to the number that you're wondering about. Which means that it's true for every n. For every n, Pn is true. So all you need to show are these two things: base case, inductive step. So, for example, show that 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared for every n bigger than or equal to 1. Show that the sum of consecutive odd numbers is n squared for every n bigger than or equal to 1. The sum of consecutive odd numbers is n squared. Right? Up to 2n from 1 to 2n minus 1, that's n squared for every n bigger than or equal to 1. Where's the predicate? So in this problem, this equation right here is the predicate. That equation there is either true or it's false for a certain value of n. Now we want to show that it's true for every value of n, at least 1. So that's the predicate. So in this Pn is equal to 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared. Right, so for example, P4 is what? What is P4? So 1 plus 3 plus 5 plus ... all the way up to 2n minus 1. What is 2n minus 1 when P is equal to 4?
7.
Well, sorry, heard something. The sound cut out.
7.
7, right? So it's 1 plus 3 plus 5 plus 7 is equal to, so when n is equal to 4,
16.
16. Which is, is that true or not true?
It's true.
It's true. Now, I don't have one in which it's false. This one is actually always true. For every n bigger than or equal to 1. But, well, P0 is not true. Well, P0 doesn't even make sense. P0 doesn't even make sense.
What about P infinity?
Well, infinity is not a natural number.
Oh yeah, that's a good point.
Yeah, it's a thing that we talk about, but it's not a number per se. There are ways to make it a number when you're talking about the set of all real numbers. That's actually fairly complicated. So we want to show that this is true. Okay, here's the proof. So first thing you do is the base case. And in here, the base case is n equal to 1. So I'll just put that there for reference. Okay, so when n is equal to 1, what does this look like? Now, I wouldn't write it like this. I would write it, what does this look like? And then what does this look like? And then look at them and say, okay, they're the same. So we're good. Okay, so if n is equal to 1, then 1 plus 3 plus 5 plus all the way up to 2n minus 1 is actually equal to what? All right, so this sum of consecutive odd numbers all the way up to 2n minus 1. Well, when n is 1, what is 2n minus 1?
1.
It's just 1. So it's just 1 by itself. Right? The first one odd number, just 1. The first two odd numbers would be 1 plus 3. The first three odd numbers, 1 plus 3 plus 5. But we kind of write it like this to show the pattern. All right, and then n squared, when n is equal to 1, is just...
It's 1 again.
It's just 1, so P1 is true. Right, 1 is equal to 1. Usually the base case is easy. Usually. Sometimes the base case is everything. Inductive step. Okay, so here we want to show that Pn implies Pn plus 1. All right, here's Pn right here. So usually, so now you can do this as a direct proof, contrapositive, or contradiction. Usually it's done as a direct proof. I've never really seen... No, I'm sorry. There is a way to do it by contradiction, but the language of it is not really the language that we're using here. That language is not something that you would use in an undergraduate level. You could, but it's not that often that one does that. So almost always this is done by direct proof. And even if you use the contradiction, that alternative language, usually it's not necessary. So we do a direct proof. We assume the hypothesis is true. We show that the conclusion must be false. In a proof by induction, you have to explicitly state the hypothesis. You must explicitly state the hypothesis. It must be the first thing you say. Okay? If you don't say it, it's not a proof by induction. It's just not written that way. Okay, so assume Pn is true, but you don't write assume Pn is true. You never actually use this language of predicate. So I shouldn't even write that. No, these are the same. I shouldn't even write that. You never actually use the language of predicates in the proof. It's just something in your mind to help keep track of things. So assume Pn is true. What's Pn? It's this. 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared is true for some n bigger than or equal to 1. And now we want to show that Pn plus 1 is true. You should write that down as well. Sometimes people don't say it. It's better if you do. I'm going to insist that you say it. So show that. So what does Pn plus 1 look like? Well, you take Pn, which is that, and you replace n with n plus 1. And then what do you get? When I replace n with n plus 1 here, 2n minus 1 becomes what?
2n plus 1.
2n plus 1. The next odd number up. Is equal to, well, now I replace n with n plus 1, I get just n plus 1 squared is true as well. Okay, this is the inductive. This statement here is called your induction hypothesis. The induction hypothesis. So that statement there is called your induction hypothesis. This right here is your target conclusion. The term induction hypothesis is more or less the standard throughout the English language usage of mathematics. The term target conclusion is my own invention for pedagogical purposes. I hope it's a good one. Okay, but the induction hypothesis must be stated explicitly. Usually people write also the target conclusion, or just the desired conclusion. Okay, I would insist that you do write it. Okay. All right, so we know this is true. We want to show this is true. And you must say where the assumption is used. Okay. This one's not too bad. 1 plus 3 plus 5 plus all the way up to 2n plus 1 is actually equal to what? Well, what comes before 2n plus 1 in this string of consecutive odd numbers? What's the
2n.
that's even. What's the odd number that comes right before it?
Two n minus 1.
2n minus 1. Right? And then the 2n plus 1 is the last one there. Okay. Well, what do we know about this sum right here? What do we know about this sum in the parentheses here? Or in the brackets? What did we assume?
It equals n squared.
It equals n squared. So this is equal to n squared plus 2n plus 1. Why? What's the reason for that there? What is the reason for this equality? Well, we assumed it's true. What's that assumption called? It's called the
Induction hypothesis.
hypothesis. And you must say that. You must say that. You must state explicitly where it is used. And then n squared plus 2n plus 1 is just equal to n plus 1 squared via algebra, as required. Right, so 1 plus 3 plus 5 all the way up to 2n plus 1 is equal to this just by, specifying what comes right before the second to last number in that sequence. It's 2n minus 1. But we assume that the sum from 1 to 2n minus 1 of odd numbers is n squared. That's the induction hypothesis. And then that 2n plus 1 is still there, and then just by regular algebra, that's equal to n plus 1 squared. Notice I'm working in a string of equalities rather than stacking equations, just like before. Okay? By the way, this statement, so side note, right, this statement 1 plus 3 plus 5 plus 2n minus 1 equal to n squared has a nice geometric proof. No induction. like, well, I mean, if you want to say n squared, like 5 squared, well, that's the number of dots in a 5 by 5 array, right? Alright, so this has got 25 dots. Well, this is 1 dot right here. This is 3 dots right here. This is 5 dots right there. This is 7 dots right there. That's 9 dots right there. Pretty cool, huh? Alright, so that's actually got a nice geometric proof. That's not something I'm holding you responsible for in the course, but you know, just a little mathematical gold nugget. Oh my goodness, it's 1:30. Gosh, sorry guys, we've gone way.